Greetings A-level chemists, welcome to a little explainer video all to do with metal aqua ion. So let's get cracking. So transition metals when in solution will exist as metal aqua ions. Not just a property of transition metals, but we're going to focus on transition metals. So transition metals, I'm going to put it up here, transition metals in solution will exist as metal aqua ions, and these will have a transition metal at the center, and they'll normally be coordinated with a ligand. So remember, a ligand is a species with a lone pair of electrons that can be donated to the transition metal center, forming a coordinate or dative covalent bond. Okay, so let's just get this down, that usually these ions will exist with a transition metal, I'm just going to shorten it to TM, at the center, being surrounded by 6 water ligands in an octahedral complex, usually. So, for example, let's have a look at, if we take copper sulfate solid and we dunk it into water, well, that's going to dissolve into copper 2+ and form SO4 2-. Now the copper 2+ isn't going to exist as isolated copper 2+ ions. It's going to exist as a metal aqua ion, and this is going to exist as Cu H2O6, and this complex has a 2+ charge. So this is going to be called hexa, because there are 6 water ligands. Now we don't call the water ligands water when we're naming for transition metal complexes, so the ligand is called aqua, so hexa aqua, and then we state the name of the metal, so this is going to be hexa aqua copper 2. You don't need to know the naming, but it's quite handy when we're studying transition metals and transition metal complexes. Now this complex is going to be a lovely light blue and gives you that characteristic color that we attribute to copper 2+. This is a light blue / cyan, and check the other videos out as to why these metal aqua ions are colored in solution. Okay, so where should we go next? So we need to know the reactions of metal aqua ions. So metal aqua ions can undergo the following reactions. So they can undergo acid-base reactions, they can undergo ligand substitution, where one ligand replaces another, and they can also undergo redox reactions. Redox reactions which involve a change in oxidation state. So change in oxidation state of the transition metal center. I'm just going to add these in. A ligand substitution where one ligand replaces another, and acid base. Remember that acid base is where we're following the proton. So a species which donates H+, so that's my acid, coupled with a species that accepts H+. And that is my base under the Bronsted-Lowry definition. So we need to know what type of reactions these guys undergo. And what we're going to focus on in today's video is acid-base reactions. Okay, hydrolysis reactions in effect. So here we've got a metal aqua ion. So we've got a metal denoted as M, and we've got 6 water molecules or 6 ligands forming dative coordinate bonds to the transition metal center. So here are my 6 water ligands, and there are my 6 coordinate bonds, and this is a coordination number of 6. So then, if we take this metal aqua ion, what can happen is, in solution, we can lose one of the protons from the water ligand. So if we lose a proton from one of the water ligands of this complex in solution, this species is acidic, because this is defined as an H+ donor, so therefore this species is acidic. And let's think about why this is the case. And this is the case because in that OH bond, I'm just going to get rid of the highlighting to make it a bit easier to see, that in this OH bond, we've got a pair of electrons. Now, let's say for sake of argument, they're here. One from the oxygen, one from the hydrogen, okay? And there is a whopping great big 2+ charge on the metal center. I know it's spread out, but let's just say it's isolated on the metal center, okay? And that is going to attract the electrons in this bond. And if it attracts the electrons in that OH bond, that electron pair is going to be pulled closer towards the metal center. In fact, it's going to be pulled towards the oxygen, okay? Because of that whopping great big 2+ charge. And what's going to happen is the position of those electrons are going to be closer to the oxygen. And so much so that we could actually lose that pair of electrons. So we can deprotonate here. So if oxygen takes that pair of electrons, we can get an equilibrium setup like this. So now we're going to have M, and it's going to have 5 water ligands around it. I'm not going to put the dash and the wedge. So we've got 5 water ligands around it. But what do we have left here if we deprotonate on that water molecule? Well, we don't have OH2 anymore. Now we just have simply OH. And remember, this is going to have a negative charge. And my metal center has a 2+ charge. So what is the overall charge on the complex now? Well, the overall charge on the complex now is going to be the charge of the metal center, which is 2+, and got to take into account the charge of the OH- ligand. So now this is going to be 2 take away 1. So the overall charge on the complex is +1. So I'm going to use square brackets here. So there is a +1 charge on the complex. Okay, it also gave out an H+ ion as well. So this is known as hydrolysis reaction. So in solution, the equilibrium is way over to the left-hand side. So this is going to be the major, component in solution, but we are going to get some hydrolysis occurring, okay? So we are going to get some hydrolysis occurring where that OH bond in the water molecule breaks and the pair of electrons is attracted towards the oxygen due to the charge on the metal center. Okay, and then that gives out an H+ ion, so this species is acidic. So metal aqua ions are acidic in solution. What sort of pH are we talking about? Typical pH around pH 6, so weakly acidic. But if we increase the charge on the metal center to make it sort of 3+ or 4+, then the acidity increases, so the pH drops. So we're making it more acidic. So metal aqua ions can also react with bases. So we need to know the reactions with hydroxide ions being added or ammonia being added in solution. So what we're going to do is let's get rid of this and then redraw, and we're going to have a look at the reactions of metal aqua ions with bases. So reactions with bases, and we're going to look at OH- and NH3. So we'll have a look at one ion in particular. So these are all equilibrium reactions. So there's two ways that we can view them. One is, I'll show you. So let's draw this out. So let's have a look at hexa aqua copper 2+. I'll draw my wedge and dash as well. So this is an octahedral complex. And for these water ligands, I'm going to draw two of them out in full, showing the displayed formula. So there we go, and there we go. And then surround the remaining spaces with OH2. And remember, these are dative covalent bonds to the metal center. Okay. So then what happens is, let's say we've got OH minus. So let's say we're only adding two equivalents of OH minus. I'm going to put the negative charge on the side of the oxygen where it should go. And remember, this species can act as an acid. And this is my base, so this is an acid-base reaction. And the definition of an acid is a proton donor, and the definition of a Bronsted-Lowry base is a proton acceptor. So what happens is, base comes along, it's more likely to react with this complex because there's more of it in solution, and deprotonate here. And that OH bond breaks. And in fact, this can happen twice. So remember, I haven't put my charge, but this has got a 2+ charge. And then we can get another deprotonation here. So that OH bond breaks as well, and look at what we get. So we will get Cu. We've got 4 water ligands now. But we've also generated 2 OH groups from the deprotonation of hydrogen from my water ligands, and I've generated 2 lots of H2O in that process, because this is the generation of my H2O. So I get 1 H2O forming here and 1 H2O forming here. So that's where we get 2 H2O, and I'm left with 2 lots of hydroxide on my transition metal complex. Now, what is the charge? Well, we know that copper has a 2+ charge. We know that copper has a 2+ charge, and each hydroxide is -1. So what happens here is that the charges cancel out. So this is my neutral precipitate. So this is a neutral complex. So this is a neutral complex, and it will form as a solid. So we get the neutral complex forming, and this is formed as a solid, and this is like a blue gelatinous, it's a good word, blue gelatinous precipitate, and this precipitates out. And some transition metal complexes will redissolve if we add excess hydroxide ions. This complex doesn't redissolve if we add excess hydroxide ions. And we get a similar reaction occurring with NH3. So we can also show it from the lens of NH3, our weak base. Okay, before we do that, I'm just going to quickly write down the reaction for this so we can write it out as this. So here's my hexa aqua copper 2+ ion. It's aqueous in solution. I'm going to add 2 equivalents of my hydroxide ion, and then I am going to make CuOH2, and I'm left with 4 lots of H2O attached, and this is a solid, and I generate 2 lots of H2O. So that's how I would write it. I'd leave the water ligands there as well, just to show the examiner you know what you're talking about. But they'd probably accept Cu2 plus 2OH minus makes CuOH2. Be very careful with your state symbols as well. So this is a blue solution going to a blue precipitate, and that's a liquid. So that's from the lens of a transition metal complex reacting with strong base OH minus. So we can do the same thing for, this reacting with ammonia. So if we do the same thing for the reaction with ammonia, you won't be that surprised. It's pretty similar. Okay. So let's get rid of these. So instead of my OH minus being there, let's put some NH3. So we get 2 deprotonations. We form the same neutral complex. this time we don't form 2 lots of H2O because we are protonating the ammonia. And if we're protonating the ammonia, we're going to get 2 ammonium ions. So this time we're generating 2 lots of NH4+, where we get the same neutral complex forming. But this time, if we add excess, if I add excess NH3, something happens. So this is when I add a limited amount of NH3. So this was a limited amount of NH3. So 2 equivalents. But if I add excess, we get a different reaction occurring. So this is acid-base, just like the previous ones. But when I add excess, we get a ligand substitution reaction occurring. And let's show this. And this is one of those funky ones you just got to remember. We don't need to know why it occurs in the way that it does. But I have hexaquicopper 2+. And if I take 4 ammonia ligands, what happens is I replace 4 water ligands with ammonia ligands. So I get NH3 4 times, and I still have 2 water ligands attached. But I've kicked out 4 water ligands. So this is not an acid-base reaction, this is a ligand substitution reaction. Just be aware of the differences between the two. So this is, I should put the charge, it's got a 2+ charge. So this is an aqueous solution, and this is a royal or deep blue solution. It's a really lovely color. So it goes from a sort of cyan or pale blue solution to a royal deep blue solution, and it's an absolutely lovely color change to observe. And this is a ligand substitution, not acid base. So remember here that the ammonias are kicking out 4 water molecules that are on the right hand side. Okay, I think that is everything. And next we're going to have a look at some complex ions and shapes of complex ions. Thank you for watching. Ta-ta.